So it's a great pleasure for me to contribute to the conference in honor of Hubert, and I'm first of all would like to thank the organizers for this great opportunity. I'm going to talk about the inhomogeneous six-vertex model, the model which is introduced 50 years ago. This is a certain multi-parametric exactly solvable model in two-dimensional classical statistical mechanics, and remarkable features of this model that it possesses a lot of parameters. And you may expect that the different type of critical behavior appear dependent on the region of parameter you choose. Well, surprisingly, there's not much known about the general situations for the criticality, except few cases, and of course the homogeneous case, which is well known. It's related to the scaling of a Heisenberg spin chain. Well, in a certain domain of when the model is critical, then described by in terms of the Gaussian field theory of three massless boson. Well, the next studied example is so-called staggered homogeneous six-vertex model, and here I would say the pioneer and the main contribution was given by Hubert with his collaborators, and the many interesting phenomena was discovered, in particular the presence of a continuous component under certain conditions, which is already mentioned in our morning talk with Jasper, and this scaling related to the conformal field theory of certain nonlinear sigma models, called two-dimensional black hole models. So then, in principle, that it's signal for that there are many interesting scenarios appeared in study of this model, and so that was my motivation to choose the subject of this talk, because I hope that Hubert would be at least interested about this, because his at least recent work somehow related to the subject of the talk. Okay, and so I would so what I'm going to do is just discuss certain conjecture which we made quite recently with Gleb Katausov about the scaling of the model, which is in fact so it's a certain generalizations of the six-vertex model. It's so-called high-spin generalization. So this is just a cartoon for the transfer matrix of the model. So and with each, so it shows that in each lattice size we have a associate with each associate defined dimensional space. And this space may be thought as a reducible finite dimensional representation of the QSL2 quantum group. And okay, so the spin here can be integer.
Spin.
Should reboot it. All right. All right. So S1, S2, and these numbers may be integer or half integers. So the case of original, the six-vertex model correspond to S equal to all S equal to 1/2. Then in the bottom you see the set of parameters which is represent the inhomogeneities. Well, and this is a transfer matrix, right? And the model depends on also on on a so-called anisotropy parameter, the same as EQ. And the critical regime is expected to be unimodular numbers. So instead of Q, we'll use gamma, which is real now. And also in the critical regime occurs as all the homogeneous is also unimodular number. All right, and so in principle, I would like to formulate a certain conjecture, and the main technical tools, the main machinery which allows one to investigate the problem. It's so-called 2D IPhT correspondence. And most part of the talk, I would try to explain what it is using the simplest example of homogeneous model. And then at the end, I will formulate the certain ODE IPhT correspondent for the homogeneous model. But from the very beginning, I should emphasize let's not give the whole description of the scaling of the model for all values of parameters. It's only on a certain domain. So let me just illustrate. It's difficult to explain, to describe the domain of parameters in general. So let me illustrate in terms of the staggered six-vertex model we already mentioned. So here is a situation. So all the spins equal to 1/2. So this is a six-vertex model indeed. And then we have the homogeneity. We have eta 1, eta 2, eta 1, eta 2, which is the patterns periodically repeated. So in principle, we can, without loss of generality, we can set eta 2 equal to inverse eta 1. Again, the critical situation is when this inhomogeneity is unimodular numbers. And so here is the phase diagram for where alpha is parameter of inhomogeneity and gamma is parameter of anisotropy. So and the regime which I already mentioned, where the scaling described in terms of conformal field theory with a continuous set of spectrum of conformal dimensions, is this the blue one, right? And this is I call it black hole domain, right? And actually, in the work of this series of work, it was studied the line AO. So it's the case the addition of the two symmetries appeared in the systems. These lines, it's already mentioned in lectures, can be the system can be made equivalently described in terms of homogeneous 38 vertex models, and if he approaches to the point O from this side, then describe the OSP22 loop model. So this is in fact, in this black hole domain, dependence on alpha is kind of very, it's this parameter quite irrelevant in the sense that not much depend on this, and it was discussed in the work of Ram and Seal. Right, so then we have parts of the case when the model actually normalized to the same as a homogeneous one to the free boson field, and the line of homogeneous line is this one, and in this case we have just the free bosons. But the subject of my interest in today, it's this line. I call it GIGM, which means generalized affine Gaden model, and we'll explain, maybe say a few words about this later. And again, the pioneer contribution to study of this domain was done in the work of Hubert and collaborators along this line, OB. Again, the system has a two symmetry, this work. And that was in principle, and here in fact, dependence on the parameter alpha becomes much more interesting than in the case of black hole domain. And that would be the subject in principle, that would be domain which is covered by my talk. But of course, it's a more general situation, I already explained. Okay, and also I should emphasize, so when you define the scaling limit, then you should you should first choose the certain state. So, certain reference state, and then consider the limit when the size of the system becomes very large, but the states should consider in the vicinity of this reference state in certain sense. And what reference state we should choose in this case? And it's convenient to choose the state as the ground state for certain spin chain, right? And the spin chain, it's defined, it's a Hamiltonian for the spin chain commute with the transfer matrix. In fact, it can be built through the transfer matrix. And here how the Hamiltonian looks like in the case of the staggered model. You see it depends on parameter of alpha and gamma. It's a less cumbersome. So this is a fast diagram for this homogeneous six-vertex model for this Hamiltonian. And so the Hamiltonian is quite complicated. So what the simplest situations when alpha is equal to 0, so we in this homogeneous regime, then it's easy to see that everything, most terms became zeros, and we end up with this only these terms, and this is nothing but xz spin Hamiltonian. And so I'm going to discuss so this is a simple situation, so let me focus on this case and discuss the basic ideas about beyond the ODE IQFT correspondence. Okay, so again, this is a usual story. So the transfer matrix, now it's a transfer matrix for usual homogeneous six-vertex model. So it built out of solutions of the Yang-Buster equations, the Hamiltonian logarithmic derivative of transfer matrix. And the only thing I would, here, I would prefer to talk about the insert in the trace and definition of trace, the some diagonal matrix, which depend on parameter k. And this matrix, as a result, the Hamiltonian, xz Hamiltonian, which appears here, as subject of the Twist boundary conditions. You see, this is exactly the parameter of the Twist. Again, so the Hamiltonian is critical when Q is unimodular. And again, I will use the parameter instead gamma. I will use the parameter beta, just historical notations, beta squared, beta in between 0 and 1. All right, and the scaling, what happens? So this is just basic formula, some simple formula which describe the scaling of the systems. So once you start the ground state and consider the low energy state, which is slightly excited state, and consider the limit, then for this state, the following famous, the state will organize in conformal towers. So basically, it shows that the state can be, in the scaling limit, can be identifying the state of the built out of the Fock space of bosonic free free massless Bose field, and P and P bar are zero mode momenta for this bosonic field. That depends on the value of the spin. Total spin operator, it's also K and W, which I call winding number. It's sometimes called vorticity, whatever, it's integers. And but you see that also the state classified according to the level inside the Fock space. L is integer, L bar also integers. It's a level, L, it's a level in Fock space FP. It's naturally graded space, linear space. And you see that if a level is large, then a huge degeneracy of the states. And the initial question occurs, what happened? Suppose we choose certain stationary state, right? Low energy stationary state, and consider the scaling limit. What would be the state inside this Fock space? It's not trivial question because there's a huge degeneracy here. Right? How to describe it? And in first, it's not even clear how to assign the n dependence to the state, because suppose you have a matrix which size n by whose size depend on n, and you diagonalize it, find the states, and how to assign suppose now we change the value of n, so how to assign the n to the stationary state? It's not clear. Fortunately, here we have certain integrable structures which allows one to organize such an n dependence for the stationary states. Because so I would say to build out the randomization group trajectory for individual states, stationary states. So dependence on the scale. Such integrable structures are well known, and namely it involves the T operators, the transfer matrix already was pictured on the previous transparency, which commute with the Hamiltonian, also Q operators with a T, which satisfy the famous TQ equations. And Q operators are up to some factor, it's a matter of convention, but it's a polynomial, right? It's a polynomial at 0, so the Q operators satisfy the beta ansatz equations. So once you diagonalize, choose the stationary state, we can resolve all degeneracy by saying that it should be not only the agent state of a Hamiltonian, but agent state for the Q operators, so T operators, all right? And now, and the presence of such, the presence of number of commuting operators in the problem allows one to, for states, so the beta state would be the states which is agent state for all commuting family of operators, and then we can indeed assign the n dependence to the beta states, for the low energy beta states. So how to do this? So suppose you have choose the number of sites, relatively small number of sites, just to build the matrix of the Hamiltonian and diagonalize it. And then diagonalize it, and then you can find the eigenvalue of Q operators on the states, and up to the simple factor, it's a polynomial, find the beta roots, right? You find the beta roots, of course, they would satisfy the beta ansatz equations. But then the point is that we can now, you find certain patterns of the beta roots for given n, but then you can consider the states, try to find the solutions of the beta ansatz equations for with increasing values of n. Let's say n, move to n plus, add additional 2 sides to the lattice, right? And use these beta roots as initial approximations for the beta ansatz equation, which contains now not n, the n replaced by n plus 2. Of course, the number of roots are different, but you just a little bit move some, add some couple roots, additional roots, and then you can start to iteratively solve this beta ansatz equation. And this procedure works. And it allows you to organize the renormalization group trajectory for each individual beta states, psi n. And then immediate questions we can address at this point: what happened with the state where n goes to infinity? And to understand it clearly, this answer required, to analysis of this answer required to analysis of the beta roots in the limit n goes to infinity. And let me illustrate the pictures for just a ground state, for the lowest energy state for Hamiltonian. So here is the typical patterns of the beta roots, namely all the roots that are real, so it's convenient to write the logarithmic forms. Theta would be logarithm of zeta, and this is represent distributions of the beta roots for the ground state. And you see the picture, so the most of the roots form the certain continuous distributions, almost continuous, all right? And there's a simple famous formula for the density of such a roots, all right? And this formula, actually, this density is would be the same for all low energy states. So it is kind of, you can choose not a vacuum, but you still get the same Cauchy, one over the Cauchy density. The most interesting phenomena happened with the roots, which is an edge of distributions. And the bulk roots will be continuously distributed, but the edge roots actually would be scaled. So you can consider the scaling behavior. So they possess the scaling behavior if you scaled it proper way. So this is Rn here, right? The numbers. So then you get the finite numbers. So for example, the first, second, and so on, you get the finite numbers. And then in the scaling limit, it means, so in the scaling limit, your beta states would expect to be the certain state in the Fock space, and each of the chiral states here would be labeled by the set of scaled root Rn for the right, let's say for the left edge, and for the right edge of the distribution, so that the numbers of the scaled root would be just label the different beta states, label the states on correspond to the state in the scaling limit. All right, but a remark how to describe these numbers. And it was a remarkable observation, it was done a long time ago, that actually this scaled number Rn coincide up to the positive constant coincide with the energy level in the certain Schrödinger equations. In fact, this Schrödinger equation is it's radial Schrödinger equations for Schrödinger equation for radial component of the anagharmonic oscillators. So the parameter of anagharmoticity alpha here, so alpha equal to 1/2, correspond to the usual harmonic oscillator. So alpha is related to anisotropy parameter beta. And also it contains, the potential contains its centrifugal terms, and the zero mode momenta related expressed in terms of, so the centrifugal potential expressed in terms of zero mode momenta. And clearly the potential, the shape of potential, we have a divergent at 0, and then it's a confinement potential on the discrete spectrum here, so that gives you descriptions of this scaled root. And so here are some numerics. So that shows, if you believe these pictures, then that shows how you should scale the Q functions in the limit n goes to infinity. So on the proper way, you redefine the arguments. And then you get certain scaling functions, and this scaling function d coincide with the spectral determinant of the Schrödinger equation. So here are some numerics. So this is a blue dots lines. It's for numerical data for 400, for 800, and so on. Number of sites, of course, rescaled. This expression represent, and then interpolations. And the black line, it's solutions. It's obtained from the solution of differential equations. Of course, some discrepancy here, but it's interpolation formula. So it's not need to. You should not expect that you get interpolation give exactly the correct answer. Okay, anyway, but all this works for the ground state. But in fact, I described for the ground state. But in fact, all this works for the excited state as well. So picture basically the same. The patterns of the zeros, of course, would be a little different. But we in the scaling limit, Q function, we get certain functions, and this certain function would be also spectral determinant, but for the Schrödinger equation with additional terms. And we call it this potential monster potentials, because it's a singular potentials. It contains the parameter VL, and the number of L actually would represent the level. So if the psi functions would be the functions would be at the level of L, then the number of the corresponding singularity would be L. And if you have a singular potential, then of course you should expect that the wave function is not single valued; it's multi-valued functions. But the remarkable features of this potential is that the wave function remain single valued. It's monodromy free. So that, in other words, it's sometimes it's called apparent. So the singularity of the potential is apparent. Well, and that makes very restrictive conditions for the position of singularities, and that leads to the system of algebraic equations. And the number of such equations is to now that coincide with the number of states at the given level of L. So in this way, you can identify the state and the level L with the level L with some monster potentials. And that property was proven. It was conjectured in our paper with Sasha and Volodya, and then proven recently by Conti and Mazzayer. Okay, and now that some bonus of all this description, that the scaling, the spectral determinant, in fact, can be identified with the eigenvalue of the certain Q operators for the quantum, so-called quantum TdV theory. So this is operators which acts in the Fock space. It's better to say not KdV theory, it's better to say KdV hierarchy, because it contains it involves the commuting family of operators, and among them the so-called local integral of motions. In the classical limit, when beta goes to 0, it's maybe interpreted as a classical limit. This becomes the classical KdV charges. All right, and but all this local integral of motion can be generated through the asymptotic expansions of the Q operator for large energy. But together with this, this is local operator. So together with local one, you can also, an asymptotic occurs also on local integral of motion, which does not have classical counterpart, and also some reflection operator, another local integral of motions. So, and this the value of eigenvalue of local or integral of motions on the scale beta roots actually useful to descriptions of finite size corrections to the energies. So the first corrections, it's in the first corrections coefficients, it's related to the first integral of motion, local integral of motion, but the higher correction involve the certain combinations of another local integral, higher local integral of motions with some coefficients which is known, calculated long time ago. All right, and here the explicit formula for the integral of motion in terms of the chiral-Bose field. All right, so so what can we learn from all of these? And principle that gives you some just a toy models for which, but which allows one to try to try to handle more difficult, complicated situations, which is I'm going to discuss in a moment. But the lesson we learned from here that scale and limit of the spin chain is related to the quantum KdV hierarchy, and the most important tools for study of the scale and limit, most useful tool for study scale and limits is this ODE correspondent, which allows one explicitly to describe the scaling corrections and do all the analytical, do some analytical works in studying the scaling limit. All right, and now, so the subject of our interest, actually, the model is more complicated, which is already formulated as an homogeneous high spin six-vertex model. So we have this one, and but first of all, we should point out that we consider the scaling limit. For this reason, it makes sense to, in the scaling limit, the system perceives translation invariance, so it makes sense to impose certain periodicity, R-side periodicity conditions. Like in a staggered case, we take eta 1, eta 2, and then periodically repeat the pattern, right? And it's guaranteed that if the scaling limit exists, then that would be translation invariance. So we impose the R-side periodicity conditions. So the number of sites should be divisible for R. This integer R, which is kept to be fixed. Some integers, maybe in the case of homogeneous cases, R equal 1. In the case of the staggered case, R equal 2. And also, this R-side periodicity should be imposed on the spins, of course. And then the questions I would like to ask here. So what would be the scaling limit when n goes to infinity? And it should be certain operators. Again, we should be careful with the domain of parameters, regime. The regime should be unimodular. The Q should be unimodular number, of course, but it's rather restrictive. Here I will introduce the integer k, which is expressed in the sum of spins along in the elementary cell, right, as a times 2. And you see that's very restrictive. So we only in this domain of parameters. In this domain of parameters, the anisotropy can be parameterized in terms of, again, beta, which is 0 from 1. So that is a regime where I would like to focus. So that is a regime of my interest here. And in our paper, we propose the differential equations which describe the scaling of Q functions. So basically, the equations look like this. This is an analog of the anharmonic oscillators. But now the situation much more involved. So we have the main terms is here, the first term. There are a bunch of other terms, but actually the main terms is here. So now, first of all, let me draw your attention that this potential, forget first about these factors. But this is a polynomial, right? And this polynomial has zeros at point A, and the number of zeros equal to R. R, it's numbers which is a defined R-side periodicity. For R equal 1, it's homogeneous. For R equal 2, it's a staggered, and so on. Then Ka, it's order of zeros, right? Ka, it's related to the spin, to S or A. The anisotropy parameter appeared only in these factors, right? In Xi, I use again its historical notations. Then Chi is related to the beta. It's convenient to write in this way because it's well. And this is an anisotropy parameter here. K, it's a sum over the K1, so it's clear. Now kappa. What is kappa? Kappa, it's something which is can be up to some redefinition, simple redefinition, spectral parameters, right? It's related to the spectral parameter Q mu of the scaled Q functions. So these terms. Then you have a terms with single the pole zeta squared. This is analog of the centripetal potential the quantum in the anharmonic oscillator. A, it's a similar play. The similar it's something which is very close to zero mode momentum p. And then you have a bunch of term which is singular, right? It may have a singularity at the point zeta A, but also may have some auxiliary singularities. And they have contains some parameters. You see JA, gamma A, capital gamma A, but all of them actually fixed by the condition that all the singularity are apparent. So they not create the monodromy. So if you drop these terms, then the monodromic property of this equation would be exactly the same as they will not affect on the monodromy of, so these terms will not affect on monodromy. So this was most important part, like in vacuum. All right, and okay, so this is differential equation. And what we proposed there, that then in domain, this domain of parameters, the Q and Q operators becomes develop the scaling behavior, and the operator T and Q actually the eigenvalue of these operators coincide with the spectral determinant. For example, for Q, it's a spectral. Again, you can define the spectral determinant. The eigenvalue of this Q operator coincide with the spectral determinant of this operator. And as for T, that also some connection coefficients were actually some Stokes coefficients for these differential equations. And what is T and Q? And this T and Q would be the operators in the certain, I would say, generalized avant-garde, better to say hierarchy. Like in the case R equal to 1, in the case, the simplest case we discussed, it was a hierarchy of the commuting operators, which is a quantum KdV hierarchy. But here it would be certain model or certain hierarchy, which we call it GAGM. And of course, the question how to build, how to explicitly construct this, because in the case R equal 1, we know how to build the local integral of motion in terms of the Free-Bose field. I give the formulas, and now how to express this, let's say, local integral of motion for this model. And for this hierarchy, actually, the natural building blocks are the currents, Kac-Moody currents. So what we need to do, we should take the R copy of Kac-Moody algebra with the level Ka, the subject of commutation. This is an operator product expansion, but it can be alternatively written as a commutation relations for the modes. Well, and for each copy, we can associate the Sugawara field or Virasoro field, that's usual Sugawara constructions, and then the simplest local integral of motions given the integrals over the local density, which is quadratically built from the Kac-Moody currents. So and this is of course only the first local integral of motion. The hierarchy, we have a higher spin, so the density have spin Lorentz spin 2. But there is a local integral of motion with the spin 4 and 6 and so on. And even for spin 2, we have not just a one integral of motion, but R integral of motion, local integral of motions. Okay, so I run over the time, so I came to conclusions. So what in this talk I discussed the scaling limit of the homogeneous six-vertex model, higher spin six-vertex model, a certain domain of parameters. And again, I should emphasize the the pioneer result when study of the system was done in the work of Iklev, Jacobson, and SALEUR for the case R equal 2 for the case staggered models in this domain, and they found that in principle the scaling can be described in terms of single boson and two Majorana fermions. And this is indeed the case in these situations. It means that we have two Kac-Moody algebra with at the level 1, and they can be realized in terms of two Majorana fermions and one bosons. This is a particular situations which we have. But I should also emphasize that in this situation, the parameters, the integral of motion actually explicitly depend on anisotropy parameters, Za. So that makes the situation different than in black hole situation when there's no such so the local integral is different. Okay, and as for the future directions, I think the model is very interesting. I'm surprised that the people didn't study this in details for the 50 years, because the future, you see, it's only a small domain of parameters of anisotropy, and there is another supplementary domains. And again, as I said, what we know only, it was studied only the case R equal 2 in this domain. I guess it's alternated spin chain. This is already mentioned, these papers, and this was related to the black hole sigma models. All right, and so a lot stuff to do, so a lot of many interesting questions. Already just preliminary analysis shows that many different type of behavior occurred, and I hope that Hubert will continue to work on these directions. It's very important because he's kind of person who know how to make the art from science. And so with the beautiful ideas, beautiful conjectures, which may be, well, not difficult to handle beside the mathematical meaning, but all this make the subject alive. Without this input, the science became very boring, well, at least for my understanding. Okay, so I wish to Hubert happy 60s, and so I hope that we still learn from you a lot of ideas and conjectures and whatever. Thank you.
Thank you. Thank you, Sergei. I have a couple of conjectures I'll tell you about.
Well, that's great.
You know, a few years ago we argued about the massive deformation by adding an extra staggering of the spectral parameter.
Yes, in the real direction,
yes.
For real staggering.
Yes, and there's an S matrix that's not
absolutely
unitary.
Right. So exactly in the so you let me use these pictures, right? So you're in the critical domain here. And if you add the real staggering, that you get some non-trivial factorization.
Yes, yes.
Well, and of course, this S matrix would consistent with the integrable structure I just mentioned. And so this is one way to study. And there is another way, the questions about this one, which is more interesting, much more interesting, how to massive deformations. I think it's related. Finally, it allows us to answer the question what happened how to quantize the Lund-Reich model.
Yes.
Well, which is an open question. Well, the people believe that's solved, but I believe there's nothing done. That's very interesting. The massive deformation here, of course, it's. And in principle, you can do this because you just stagger it in the real directions and do numerics and see what I think it's a really great opportunity to.
Okay, but you have not thought of it yet.
Yeah, but you know, we have too small resources to study. But of course, this is even staggered case. A massive deformation would be very, very interesting, especially here.
So something happened with the online part of your seminar, so my concentration went a bit away into the computer. So I'm a bit ashamed to ask a question. Maybe you discussed it for 10 minutes. Did you do anything about higher periodicities of the staggering?
Higher periodicity, the three. For example, you can do R equal 3. So what we did, let me explain. That's what happened there.
Well, first
so
tell me honestly, did you talk about it for 5 minutes, or?
I don't. Maybe yes. So that's indeed interesting questions, because in the case of this domain R equal 2, right? The patterns of beta roots actually we have two lines of beta roots, and the difference between doesn't depend on anisotropy on homogeneity parameter. This is what's demonstrated by Fram and Seal, right? And it's stable, and basically that means so dependence on alpha. It can be absorbed in the definition of coupling constant. So that is the domain actually that doesn't depend on. You can use alpha. The value of alpha is not essential here. But for even the 3 case, you see that the patterns of beta roots depend on alpha, the strings. And that makes, I don't have an idea at this point, you know. But if to study this case, to understand what's happened, then principle, that's all this business with differential equation can be immediately done. Yeah, just see the dependence, how depends the patterns of beta roots, just for ground state, how it depends on anisotropy, on homogeneity parameters. You have 2 homogeneity parameters there, and how they move, and they depend. You clearly see the dependence. No, we have three lines of zeros, right? In this case, we have 2 lines of zeros, right? And they're stable when you change the alpha. The difference between pi over 2, and that's it. But for when you have R equal 3, then the difference between the lines of zeros and depends on alpha, depends on homogeneities, and it makes and also you clearly see the 3 uncompact bosons here, 2 uncompact bosons and 1 compact. That's clear. And what is this, and what integrable structure behind this? I don't have an idea. So that a lot of questions immediately.
All right. So if there are no other questions, let's thank Sergei again.
Mm-hmm.